All right, so we touched on this in the last chapter, and I told you this part already, that every chromosome has hundreds to thousands of genes on it, and that means that it's possible that sometimes you could have two genes that are on the same chromosome. And if they're on the same chromosome, they're not going to show independent assortment, and they're going to be inherited as sort of a package deal. They're going to be stuck together, and that's called being linked. So in this chapter, I want to show you how we can apply that to actually like numerical data. So in this slide, what they're trying to show you is that these genes in fruit flies are linked. So you'll see how B with a plus, VG with a plus, that's the wild type, are on one chromosome, and then little b and little vg are on another chromosome. So I'm going to switch over and show you this slightly differently and try to give you sort of a walkthrough of what I mean. So here's what they're going to probably show you on an AP exam. So let's say that you have these genes. We're going to use big B for black and little b for white, and then we're going to use big V for normal wings and little v for vestigial wings. So we have this fly that is black this is eyes, and normal wings. And what we're doing here is what's called a dihybrid test cross. Remember, a test cross, you cross with a homozygous recessive. So we're crossing this one that's heterozygous with a homozygous recessive. So this is one that's got white eyes and vestigial wings. Vestigial actually just means like they're like shriveled up. Now, if these two traits are not on the same chromosome, in other words, we've got B and V on one chromosome and little b and little v on another chromosome, then when this goes through meiosis, what I have here are all the possible combinations of B and V. We did this in the previous chapter. Now I know in the past I've shown you this with the product rule, but I want to show you a Punnett square for this instead. So this is the 4-box Punnett square. So here's what we would expect in our dihybrid test cross. This is our recessive one. It's always going to give little b and little v. And our other one can give 4 possible combinations of b's and v's. And here they are. So big B with big V, big B with little b with big V, little b with little v. All 4 combinations. Here's our expectations from this cross. We would expect 1/4 of each. 1/4 of the flies come out black and normal. 1/4 come out white and vestigial. 1/4 black and vestigial, and 1/4 white and normal. So we would expect even numbers of each. In real numbers, if there were 1,000 flies, we would expect 250, 250, 250, 250. On top of that, we would also expect, I've grouped these together, these two would be called parental types. And this is important. We haven't used this terminology before. They're called parental types because they look like one of the parents. Black and normal is what one of the parents looked like. And white and vestigial is what the other parent looked like. We call these two recombinant types because they don't look like either of the parents. They have the opposite combination. Black, which is what parent 1 had, with vestigial wings, which is what parent 2 had, and the other one is the opposite, white, and then normal wings. We can combine this, and we see that about 50% of the offspring look like the parents, and about 50% come out as recombinants, okay? So this is what we would expect. Previous chapter, you could do Punnett squares on this, and you would expect 1/4 of everything. We did actually several crosses where that was the answer. And then, on top of that, if we combine these, 50% look like the parents, 50% recombinants. Now, on the right side, this is what happens if the genes are linked. So now these two genes, B and V, capital B and capital V, are on the same chromosome. So I did it again as a Punnett square. You can't use the product rule for this actually because it doesn't follow independent assortment. So the only 2 options are capital B with capital B, little b with little v. Why? Because since big B and big V are on the same chromosome, they're inherited together. So what would be our expected if the genes are linked is this. Half of the offspring black and normal, the other half of the offspring white and vestigial. Out of 1,000, we would have expected 500 black and normal, 500 white and vestigial, And notice that all of them look like one of the parents. None would show recombination, meaning a new mixture. Now, here's the thing. If we go to a real cross, what we're going to see, if genes are linked, is that we're not going to see either one of these results. We're not going to see equal numbers of everything, but we're not going to see no recombinants either. So I put two questions here. These are both from previous AP exams to show you what you would see when they want you to know genes are linked. So let me move this one out of the way and make this one in the middle. So this one is explaining a whole thing, Drosophila melanogaster, that's the fruit fly. And they're looking at vestigial wings, which is the dumpy or the shriveled up wings, and cinnabar eyes. It doesn't matter what the genes are. It explains that little VG is vestigial wings, and the regular is normal wings, and then the recessive on the eyes are called cinnabar, and the dominant are bright eyes. Here's the bottom line. It says you started with a female that's wild type with wings and eyes, so she's like basically this, crossed with this. And then it says all the F1s, which are these, are crossed with recessive, basically this. So remember what I told you. If the genes are stuck together, we should expect all of them to look like the parents. And if the genes are not stuck together, we would expect about a quarter of each. Look at the results we get. 226 look like this parent. 223 look like the other parent. And here are our recombinants. Now, why do we have recombinants? My point is this. If we had gotten all four about equal, we would say the genes are on two different chromosomes. If we get this result, where almost all of them look like one of the parents, and a few are recombinants, we say the genes are linked. Where are the recombinants coming from? They're coming from crossing over. And the lower the percentage of recombination, the lower the number of recombinants, the closer together the genes are on the same chromosome. So the question here, which of these explains it? They're on two different chromosomes? No. They're sex-linked? No. They're on mitochondrial DNA? No. The two genes are linked on an autosome. That's your answer. And now look at this other question. Same exact thing. So now we're going to move to this one. Again, this is from the 2016 exam. Here we go. Fruit flies, blah, 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 blah. Here's the expected results. Same cross. It's a dihybrid test cross. Expected results, the same number of each. Instead, what do we see? Most of them look like one of the parents, and then these low numbers of recombinants. What causes this? Again, look for the choice that says something about them being linked. So let's see. They sort independently? No. That would mean they're on different chromosomes. They're located close to each other on the same chromosome. There it is. This one, dominance, and this one talks about males and females, and there's nothing even about males and females here. So there it is, linked. So bottom line, when two genes are linked, what they'll show you typically is a dihybrid test cross, heterozygous with a recessive. The expected on that cross is equal numbers of each thing, and about 50% look like the parents and 50% recombinants. If you get most looking like the parents and only a few recombinants, like let's say 10%, 17%, 5%, it means the genes are linked. And the lower this number is, the closer they are together on the chromosome. In fact, 5% recombination, they'll say they're about 5 map units apart. 12%, they're about 12 units apart. They literally determine how far apart they are by how much recombination occurs. So hopefully that is an explanation for you of how sex-linked traits, or how linked traits work.